This video is going to look at combining functions using algebraic methods and composition of functions. So we want to be able to combine functions algebraically, combine them with composition, and to be able to find the domain of a combined function algebraically or composition. When we're combining functions algebraically, it's pretty straightforward. If we have two functions that we're trying to add together, we just take those two functions, put a plus sign in between them. If we are subtracting two functions, we simply put a subtraction sign in between them. We have to remember to distribute the negative if necessary. Multiplying two functions together, just again remember to distribute if necessary. And if we need to find the quotient of two functions, we put one function over the other, and then we're going to have to pay attention to what happens to my denominator, because remember, my denominator can never be 0. So an example here, we have f of x equals x squared and g of x is the square root of x plus 1. So we're going to look at combining some functions. So the first thing we're going to do is find f plus g. So this is really just f of x plus g of x. So I'm just going to take the f function, which is x squared plus, and then the square root of x plus 1. I can't simplify anything there, so that is my answer, and we can just leave it like that. We're going to do f minus g, so again, similarly, this is just f of x minus g of x. So we have x squared minus, and then again, the square root of x plus 1. If we're multiplying f times g, then we're going to have f of x times g of x. So we have x squared times the square root of x plus 1. Again, not too much to simplify there. We could do a lot of algebraic manipulation, but I think it's fine to just leave that one just like that. Remember, up here it also asks us to give the domain of each of these. So if we come up here, the domain of the f function is simply all real numbers because this is a parabola. The domain of this g function is going to be the values from -1 to positive infinity, because the quantity x plus 1 has to be greater than or equal to 0, so x is greater than or equal to -1. So when I combine two functions together like this, I'm really just looking at the overlap of these two functions, so I want to find any number that is contained in both of those. So if we think of that visually, the f function is everything along the number line. The g function is this section of the number line, so what part of the number line is contained both in the light blue section and the green section. So for all of these, my domain is going to be -1 to infinity. Now when we start looking at division, we have to be a little bit more careful. So if we do f over g, we're going to get x squared over the square root of x plus 1. So here we're going to start with this same domain of the combined functions, so -1 to positive infinity. Then we have to think about what's going to make the denominator 0. So if I plug -1 in for x, then I'm going to get the square root of 0, which is 0, and we can't have 0 in the denominator. So in this particular case, x cannot be equal to -1. So I have to remove -1 from my domain. So my domain is going to look similar, -1 to infinity, but this time we're not going to include the -1, so we're going to have parentheses there. If we look at the quotient the other way, g over f, we're going to get the square root of the x plus 1 over x squared. In this case, what's going to make my denominator 0 is the number 0, so x cannot be 0. So now we're going to come up to the number line and we need to remove the value of 0. So we just kind of need to take out the value of 0 from that blue region there. So now here my domain is going to be -1 to 0. I can include the -1 this time because although it will make my numerator 0, it doesn't make my denominator 0. And then all of the numbers from 0 to positive infinity. So looking at combining functions just in some word problem formats. So we're planning a car wash here. Our initial cost to be $220, and it will cost on average 50 cents to wash each car. We're planning to charge $10 per car, and we have received a donation of $50. We do not have a predicted number for the number of cars that we think will pay, so we're going to call this our variable, and we'll call that X. So write a function for the cost of the car wash using X to represent the number of cars. So the cost for the supplies is $220, and it's going to cost on average 50 cents for each car. So for A, my cost function, I'm going to use C to represent that. So my cost function is going to be $220 plus 0.5x. B says write an income function. So we're planning to charge $10 per car, so we're going to get $10 for every car, plus we received a donation of $50, so that would count as income. So my income function can just be 50 plus 10x. And then C, we want to write a function for the profit. So my profit, remember, is going to be all of my income minus my costs. So for C, my profit function is going to be my income function minus my cost function. So my income function, remember, was 50 plus 10x minus my cost function. I'm putting this in parentheses here so that we remember that we have to distribute the negative. So just simplifying here, we've got 50 plus 10x, distribute the negative, and we end up with a profit function of negative 170 plus 9.5x. Similar question, we are working to clear a field for a new vegetable garden. We currently have a field that's 3 meters by 2 meters, and each week we're going to expand the area by 1.5 meters in length and 1 meter in width. So if it helps you to kind of think of a picture here where you have a rectangle that is currently 3 by 2. We have a rectangle that's currently 3 by 2, and then each week we are expanding the length by 1.5, so we're going to add 1.5 each week, and I'm going to call that x for each week. And then the width is being increased by 1 each week, so just by x each week. So actually our diagram has kind of helped us figure out A and B, so write a function for the length of so my length function is 3 plus 1.5x. My width function is 2 plus x. And then C asks us to write a function for the area. So area of a rectangle is length times width. So I'm going to take the length function times the width function. So we get the 3 plus 1.5x times 2 plus x, and then we just need to simplify. And we end up with 6 plus 6x plus 1.5x squared. Next, we want to look at composition of functions. Remember, there's two different notations for this. So this is the F circle G notation, which you should have seen in Algebra 2, along with the parenthesis notation F parenthesis G of x. I will typically use the parenthesis notation, and I rewrite the circle notation anytime I see it. I think that the parenthesis notation makes a little bit more sense and is typically what you would see more often when you moved on to calculus. Remember that composition of functions is simply about substituting and simplifying. So you always start from the inside out. So the first thing that you always have is your variable x, and then you have your inside function, so you do that first, g of x. Once that is evaluated, then you evaluate the outside function, which is f. So that's how you can get f of g of x. So always start with your inside function, simplify it as best you can, and then you take that and plug it into the outer function, and then again simplify as best you can. The diagram here at the bottom talks a little bit about the domain of the composite function. So x must be in the domain of g, and g of x must be in the domain of f. So it gets a little bit confusing, I think, when you think about it this way. So my advice is, if you need to find the domain of a composite function, to find that domain once you have completed the composition of functions, but before you start to simplify anything. So just looking at evaluating some functions, with composition here, we have f of x is x squared plus 3x, and g of x is x minus 2. So we're going to kind of think of the f function as the green function and the g function as the blue function. So first we're asked to evaluate f of g of 4. So remember, composition of functions is about substituting and simplifying. So inside my smallest parenthesis, I have 4. There's nothing I can do to simplify that. So now I'm going to take the 4 and I'm going to plug it into the g function. And the g function says take what's in the parentheses and subtract 2 from it. So we're going to go 4 minus 2. At this point, I want to simplify. So this is going to give me f of 4 minus 2 is just 2. So now I've simplified in the smallest parenthesis that I have currently. So now I'm going to take the 2 and I'm going to plug it into the f function. So that says that I'm going to take whatever is in the parentheses and square it, plus 3 times whatever is in the parentheses. And that's going to give me 10. So now we're going to work in the opposite direction. We're going to do g of f of 4. So similarly, we're going to start inside. 4 is simplified, so I'm going to plug 4 into the f function. So I'm going to get 4 squared plus 3 times 4. So this is going to give me g of 4 squared is 16, 3 times 4 is 12, so that's going to give us 28. Now we're going to take that 28 and we're going to plug it into the g function, which says take what's in the parentheses and subtract 2, which will give us a 26. Notice that here we switched the order of the composition and we did not get the same answer. So this is a counterexample here to the statement about composition of functions being commutative. So remember, the commutative property says you can switch the order around and you'll always get the same answer. Here we have one example that shows us that that is not always true. So what we know is that composition of functions is not commutative. All right, working similarly here, we have the same 2 functions, but we're going to do a composition of functions with finding the rule. So we're doing just f of g of x. So again, I have f of, and then we're going to do the inside function as g of x. So here we're not evaluating. Remember, we are finding a rule for this composition. So we still have f of, and then my smallest parenthesis is x, and it's completely simplified. There's nothing else we can do with that. So here, we're just going to substitute. Instead of writing the g of x, we're going to write its rule, which is x minus 2. Then we're going to write the f function, which says take what's in the parentheses and square that, plus 3 times what's in the parentheses. And currently what's in the parentheses is the x minus 2. So I'm going to put that in both places. Here we're just going to simplify, so x squared, or x minus 2 quantity squared is going to give us x squared minus 4x plus 4. Distribute over here, so 3x minus 6. Combining our like terms, we're going to get x squared minus x minus 2. Again, we're going to do the opposite order here, so now we're going to do g of f of x. So we're going to do g of, again, my smallest parenthesis is x, completely simplified. So now we're going to replace f of x with its rule, which is x squared plus 3x. So now we're going to write the g function, which says take what's in the parentheses and subtract 2 from it. And currently what is in my parentheses is x squared plus 3x. Nothing really to simplify here, except we can get rid of the parentheses, so we get x squared plus 3x minus 2. Again, comparing our results, we can see that these are not the same expressions, so we again have a demonstration that composition is not commutative. We want to find the domain of each of these. So remember, my advice is when you're trying to find the domain, use your rules for finding domain and do it before we simplify anything. So I'm going to go back to here before I started simplifying anything, and I'm going to ask myself my questions about domain. Is there a variable in the denominator? No. Is there a variable after log or natural log? No. Is there a variable under an even radical? No. So then that tells me that I know that my domain here is all real numbers. Same thing down here with the second example. Before we simplified is here. No variable in the denominator, no variable under an even radical, and no variable after log or natural log. So my domain is, again, all real numbers. So again, kind of a word problem example of this composition of functions. So we're shopping for new shoes, and the store has a 25% off sale. We also have a coupon for $20 off, and the sales tax rate is 6.75%. So first thing we're going to do is write a function f of x for the cost with the discount only. So f of x is a 25% off sale. So remember, if 25% off, we're actually paying 75% of the price. So my simplest way to represent that would be the cost of the shoes with the discount is 0.75x. write a function for the cost of a pair of shoes with the coupon only. So we have a 20% off or $20 off coupon. So my g of x would just be x minus 20. And then finally write a function h of x for the cost of the shoes with the sales tax. So here my sales tax is 6.75%. Remember, with the sales tax, we're keeping all of the cost of the shoe plus an additional 6.75%. So that's 1.0675 times the cost of the shoe, which is x. And then for part D here, we're going to write a composition function for the discount, the coupon, and the sales tax, and we want to do it in that order. So our final cost for the shoes, the discount is the f of x, so that's going to be first. Then the coupon, so that's my g function, so that's going to come next. And then finally the sales tax, so that's my most outside function. So now if we just start simplifying here, so first we're going to have h of g of, and then my f function, which is 0.75x. So then next we're just going to have h of, and now we're going to plug the 0.75x into the g function. So we're going to have 0.75x. So we're going to have the 0.75x and then minus 20. And then finally, we're going to plug that into the h function, which is 1.0675 times what's in the parentheses here, which is 0.75x minus 20. And simplifying, that gives us, so we end up with the function 0.800625 minus 21.35 times x. All right, last thing with combining functions is to actually decompose functions. So we want to be able to figure out what functions we combine together to get this composition of functions. So one thing that you can look for when you're trying to decompose a function is if you have an expression that repeats. So example, in here we have the x plus 1, which is repeating. So if we think about that, that's probably my inside function, so that becomes the g of x function. So in this case, we're going to say g of x is the expression x plus 1. And then if we just think of that x plus 1 as a giant x, then that's really going to give us our outside function, which in this case is the f of x. So my f of x function is going to be x squared minus 3x plus 4. And then if we think about this, if we do f of g of x, then we're going to do f of x plus 1, which means we're going to rewrite the f function, except every place there's an x, we're going to write x plus 1, which gives us x plus 1 quantity squared minus 3 times x plus 1 plus 4, which is exactly what we started with. So then we can see that these are the functions that we could start with to end up with that answer. Over here on the second example, we don't have anything that is repeating itself, but we do have this function here, x cubed plus 1, which is inside another function, which is the absolute value function. So we can just kind of think of it that way. So in this case, my g of x function is going to be the x cubed plus 1. And my f of x function is going to be absolute value of x. Again, if we combine those together, so if we do f of g of x, we get f of x cubed plus 1, and that tells us that we're going to take the x cubed plus 1 and plug it into the f function, which is absolute value of x cubed plus 1, which is exactly what we started with. So again, that confirms for us that these are two functions that we could decompose from the original function. There are different answers that you could use for this one, so this is not the only answer, but this is probably the easiest one that you could come up with.